Hash table is one of the most important and widely used data structures in programming. But very few people know how does a hash table internally work. Hi, my name is Prateek, and in this tutorial we'll understand the internals of a hash table and concepts like rehashing, load vector, and many more. And why the operations like insertion, deletion, search are considered as order 1 operations on average. But before we dive into the tutorial, make sure you check out Scalar's masterclass on the event page where you can learn from industry leading experts. Also, subscribe the channel if you haven't done already. Let's begin with the tutorial. Let us try to understand what is a hash table and how it works. Okay, so you might be already using hash table a lot of times, and it is known by different names in different languages. For example, in Java it is called as hash map. In Python, it is called as dictionary. In C++, it is called as unordered map, right? So there are different names, but the internals of the data structure, they are same in different languages, okay? So hash map in Java, dictionary in Python, and unordered map in C++. And in, of course, in other languages as well, you have this data structure that is available, right? So the reason why we are going to study this data structure is it is very, very powerful, right? And it is used a lot, right? It is used a lot, right? So when I'm saying it is used a lot, so not just business logic. So when you're dealing with your problem solving, when you're building real software, you would often require a hash map to store data in the form of key value pairs. Okay, so it stores information in the form of key and the value pairs. But not just that, we can also store key value pairs in the form of a list, right? Why it is powerful? Because it allows us to do operations like insertion. I want to insert a key value pair. I want to look up for a particular key, right? And maybe I want to delete a particular key, right? A key value pair. So I can just give, okay, this is the key, delete the corresponding value and the key. So delete the key value pair given the key. So lookup means the search, right? I want to search for a particular key, if it is present or not, and if it is present, what is the associated value with that particular key, right? So these are the three important operations associated with the hash table, right? And the good thing about these operations is why this is so popular or why this is so powerful, because these operations are performed on an average in order one time. So order one on average, that means most of the times these operations will be performed in constant time. Okay, so we will discuss the scenario when they are not performed in constant time, but you can say, okay, most of the practical scenarios, these operations would be performed in order one time by the hash table, right? So now let us discuss where this can be used. Okay, so I discussed that it stores information in the form of key value pairs. Okay, suppose you are building a application for a restaurant, and user of wants to order particular item, right? So user says, okay, I want to check if dosa is available and what is the price of the dosa. The restaurant owner might instantly reply that, okay, the cost of the dosa is 100, right? So given this key, you are telling the value in order one time. Okay, maybe I want to order some coke, maybe this is priced at 50, maybe I want to order some noodles, right? This is costing maybe 70, right? So what can happen with this menu? What are the operations we might be doing on a restaurant menu, right? So if we are building an online menu, we might be adding a key value pair. Okay, a new item has been added, maybe a pizza has been added, so you will supply, okay, pizza has been added and it is associated with some object, or in this case that object is nothing but an integer object only, right? So the cost of pizza is 250, right? So I can say I want to insert a new key value pair, that is doable. Second is I can look up. Now I can ask what is the price of the coke. So the hash map will tell me in order one time, yes, the price of the coke is 50 rupees. Then I can delete. I can say, okay, coke is not in the stock, delete coke. So it will be deleted from the table. So these are the three operations that our hash table is going to support, right? Now, of course, we saw that this can be used in business logic. When you're building an application, a hash map can be a useful data structure to use, right? Because it provides fast lookups, fast inserts, and fast delete operations as well, right? But one major application is also in the language runtime, right? So whenever you are working with a language like Java or C++, you know, you create certain variables, create certain classes. So you say, okay, I'm going to create a variable int x, and I'm going to say this is 10, right? Then you say, okay, int y, this is 20, right? So what happens is how these variables are stored. So these variables are actually stored in the memory, right? So X is a bucket that is storing 10, Y is a bucket that is storing 20, right? But when you want to make a change, you want to say, okay, X is equal to X plus 2, right? So your compiler needs to know where is this X located so that it can go to that location and change that bucket. Now, suppose this bucket is at some address ABC, right? Let's say ABC20, right? This is some address written in a hexadecimal format, right? So the compiler maintains a symbol table for all the variables and the classes that you are going to, all the objects that you are going to create. So there is a symbol table, right, maintained by the compiler, right? So this symbol table will tell that, okay, X is a bucket which is present at this location ABC20, right? Now when you do this operation, X is equal to X plus 2. So I'll just scroll up a little bit. When you're doing this operation, x is equal to x plus 2. So the compiler will look at the symbol table, where is x located, it will go to that location and it will make the change, right? Similarly, y is located at some location, maybe 11462, right? And maybe, right? So 11462. This is some other location for y. So y will, it will again look up at the symbol table, where is y located, it will go to this location and it will make the change in the y, right? Similarly, if you create some objects, let's say dog d, this is equal to new dog. So this dog object is created at some location in the heap, right? So similarly, your d will be mapped with some address, right? Now, what is your symbol table? A symbol table is also of a form of a hash table, right? It is also a form of a hash table, right? That your compiler is maintaining, and it is called as symbol table, right? Similarly, when you have classes and objects, right? So you say, okay, I want to create a new class called dog. The dog has certain properties, right? Let's say it has a certain name, it has a certain breed, it has a certain method, right? So what is happening? So you're able to map dog with various attributes and various methods, right? So all these features, right, they are powered by the language runtime, and language runtime might be is actually using hash table internally, so that you can do lookups very fast. Okay, if this functionality is slow, your language will become slow. So that is another application of hash table. It is used in the internals of the language. So I hope you got a good introduction about hash table. Now we will jump into the internals of the hash table. So let us talk about hash table internals, right? So what is exactly a hash table from inside? Basically, it is nothing but it's a container. Okay, it's like, in the simple form, it can be an array as well, okay, of some size, right? So basically, whatever data we are given, we have to map this data with a certain index in this array, right? So suppose I'm getting dosa, right? So the first step of a hash table is that we have to hash the key value, right? We have to produce an integer location for a given key. Now, given key, in this case, I'm taking it of the string type, but it can be any object, right? It can be student, it can be book. So for that particular type of object, you need to tell the hash function how that integer value will be computed, right? So right now I'm assuming that there is a hash function which is going to accept some key, let's say dosa, and it is going to produce an integer location, right? So maybe that integer location is 0 1 2 3 4 5 6 and so on, right? Maybe dosa will get stored here, and the value will also get stored here, right? I got noodles, so noodles will go into this, and maybe I get a location 6, so maybe noodles get stored here and 150 gets stored here, right, in the same location, right? So what is this hash function doing? Hash function is taking input a key, and it is producing a integer location in the array, right? Now you might have some questions, right? How big this array should be, right? Now if I have six keys, and if I have six, let's say six size of the array, right, and I have 12 keys, then of course I cannot store 12 keys in this array, right? So it's going to cause problems. So we will look at how to handle this very soon, right? This is not the completely correct implementation. We are going to discuss it step by step, right? So the idea of hash function is that it is going to produce a unique integer location for every key, but it is also possible that for two different keys they get mapped with the same location. For example, if I get something like Coke, and this since this is a mathematical function, it might compute similar location as well, right? So it might say, okay, Coke should also go here, right? So this is called as a collision. We will discuss how do we handle collision, right? So maybe 200 something, but the idea is how big this array should be, right? So one thing we need to note is that if it is producing an integer, then integer can take any value, right? So integer can be in the range maybe 0 to 10, it could be in the range 0 to 100, right? It could be even in the range of 0 to int max, right? So that means, like, if I talk about every possible integer that can be generated, this range can be int max as well, right? But do I really need to create this big array? Okay, int max is approximately 10 power 9 elements, right? If I talk about how much space this array will take in the physical memory, this will come out around 16 GB, right? So will you need 16 GB of an array, right? Or can you create this big array? The answer is definitely not. We cannot create this big array because this amount of continuous memory might not be available. And secondly, suppose you have created this big array and you have only 1000 keys in your key value pairs in your dataset, right? Then you are allocating space for 10 power 9 elements and you just need space for 10 power 3 elements. That means you are doing lot of space wastage, which is not a good option, right? Then how big this array should be? It should be roughly of the order of number of keys that you want to insert, right? So if you have an idea, okay, I want to insert somewhere around 1000 keys, then it is good enough. This array should have around 1000 buckets inside it, right? Or if you want to insert maybe around 500 keys, it should be of the order this much, right? So what I'm going to say, that table size should be of the order number of key value pairs that you're going to expect, right? Now it might happen that you expected 500 keys, but in practice, since the data was dynamic, 700 keys came, right? So we will also look at techniques to grow this table dynamically during the insertion process, right? So that is something we are going to study, right? What happens if there is a collision? How do we grow the table? How do we initialize the table? So all these concepts we are going to see next. So let's begin. Starting with the hash function, we will talk about insertion, searching, and deletion in the hash table. So we are discussing hash function, right? So as I discussed, hash function can accept a key. Okay, input is a key. It can be of any it can be any type of object. For our case, I'm just assuming it to be a string, and I want an integer value in some range. Okay, in some range that is from 0 to n minus 1, where n is the size of the table, right? So n is the size of the table that I am implementing, right? So for example, just to keep things simple, I'm going to assume that I have a small table where the size of the table is just 7. So 0, 1, 2, 3, 4, 5, and 6. So indexing is from 0 to n minus 1. So I have this array, right? Or I call it as table as well. So this is having a table size of 7, right? Now I have a hash function which knows how do I convert a given string into a numeric value. So suppose I'm getting a key like dosa comma 100, right? The goal is to generate a integer, map it with an integer, right? And that value should not be random. It should be same always. So whenever you ask dosa, you have to tell me at what location this dosa is present, right? So goal is to convert this dosa into a number in the range 0 to 6, right? How do I do it? So one simple way could be that I iterate over the ASCII values of dosa, add them, and since this addition will produce a number much larger than 7. Okay, for example, your capital A, right? I think it has a ASCII value of 65, B is 66, C is 67, so D will be 68, right? So similarly here you will have certain values, 68 plus something plus something plus 65. This is going to produce a large integer, right? Maybe of the order 200 to 300, right? But I want to map it in the range 0 to 6, right? So what I will do, how do I reduce a bigger range, which is some larger range, into a smaller range, right? So I can say, okay, fine, this can be easily achieved by using a mod operator, right? So I can say mod with n. So I can take a mod with n. So let us assume that this mod gives us an answer that is 4. So that will be called as a hash index. Okay. So basically the index on the table produced by hashing, the hash index is, let's say, 4. So that means DOSA will go at this particular index and this value will be stored at this place, right? Now the question is, what should I do? Maybe I am getting another key, right? In which the result is also 4, right? The result is also 4. So can this happen? The answer is yes. So I can say, okay, I have maybe Coke and maybe 150, right? I do not know. I add the letters of Coke, right? And I take a mod with n, right? Now, mod with n can produce the same result for many numbers, right? So maybe this also leads to 4. What, what happened here, right? What happened here? So Coke is also fighting for the same position. That means I also want to store Coke here, right? Now this thing is called as a collision, right? We have space for only one key value pair, but we want to store maybe two or more key value pairs at that particular location, right? So this is something called as a collision, right? So what happens, right? So what is a collision? A collision is a scenario in which basically two key value pairs, two or more key value pairs, they get with the same bucket, mapped with the same bucket. So this, what does this mean, right? Can we avoid collisions? The answer is no. Can we reduce collisions? The answer is yes, right? So we will talk about both the things, right? So in order to reduce collisions, right, what we need is we need a good hash function. So we will work on both the fronts, right? So collisions should be, it they cannot be avoided, right? So how, irrespective of how good a hash function is, collisions cannot be avoided, but they need to be handled, right? So cannot avoid collisions, right? Okay, but I can reduce the chances of collisions, but chances of collisions can be reduced by using a good hash function, right? But chances of collisions can be reduced using a good hash function, right? Using a good hash function. Now, how do we design a good hash function? We will discuss by taking an example of string, right? And secondly, since you cannot avoid collisions, so even if the collision is happening, you need a way to handle that collision, right? So they still need to be handled. So we need something called as a collision handling scheme, right? Collision handling scheme. This is something we will discuss very shortly, right? Now there are two important things here. One is what is a good hash function. A good second is we need a good collision handling scheme. So first, good hash function will reduce the chances of collisions, but they still can happen. So if the collision is still happening, we need to handle it using collision handling scheme. So let us discuss how do we design a good hash function and how do we design a collision handling scheme next. So let us discuss the properties of a good hash function, right? So I am going to discuss the properties of a good hash function, right? So basically a good hash function should have two properties. First, it should ensure a more of a uniform distribution. Okay, it should ensure more uniform distribution, right? And secondly, it should be fast to compute, right? So that means we do not spend a lot of time in computing the hash index itself, right? For example, in our case, what we were taking, I will take examples of two hash functions. Okay, so let's say example number one. in which I'm simply adding the ASCII values and taking a mod with the table size. So I'm saying fine, I will add dosa d plus o plus s plus a, and I will take a mod with the table size, right? Now, is this function fast to compute? Yes, because I just need to iterate on the letters of the key, right? So when I'm talking about, I'm going to insert many key value pairs. So what is n? N is the number of key value pairs. Okay, so key 1 value 1, key 2 value 2, right? Key 3 value 3. So I want to insert many key value pairs. So my hash index does not depend upon the value n, but it depends upon how big my key is. So in general, the key would be small length. So we can assume that, okay, if it is a name of a person and the phone number as the value, the key would be maybe maximum 50 characters or 100 characters. So yes, in this case, this is a fast hash function, right? But is this hash function is going to minimize the chances of collisions? Maybe not, right? Why? Because if I talk about English language, right? In English, lot of words, they are anagrams. That means lot of words have same set of letters in them. For example, let's say the word is tab, right? So it is made up of T, A and B, and if you add, you will get certain sum, right? But if I talk about the word bat, right, it is also made up of same letters. So in this case, we are sure that these two are going to collide because our hash function is doing a very simple sum, right? So in maybe, of course, there could be other words also. Maybe the word is mango, right? Now it is possible that even if you do a mod with table size, you might end up at the same index, right? So we do not know. So in this case, it is of course difficult to tell whether the collision will happen or not, but it may still happen, right? But here we are sure that a collision will happen, right? So many words in English, they will have such a scenario, right? What we can do is, instead of doing a simple addition, right, we can do a weighted addition, right? So this is like a simple addition of ASCII values we are doing, right? So a better way would be that you do not do a simple addition in your hash function, but you do a weighted addition, right? So example 2 of building a hash function would be that you do some weighted addition, right? So that means you are going to multiply each letter's ASCII value with some weight, right? So for example, I choose a weight, maybe generally it is a prime number, right? So maybe I choose a weight as, let's say, 31, right, or 29, right? So what I can say that fine, I will multiply dosa with powers of 2. So let's say the weight is 29. So 29 power 0, that is 1, into D, plus 29 power 1 into O, plus 21 square into S, plus 21 square into A. And then I take a mod with table size, right? What I'm trying to claim is, now if you do it for bat and tab, it is less likely that you will have a collision, right? So I'm saying you multiply 29 power 0, which is 1. This is 29 and this is 29 square, right? And then you, like, it's a weighted addition. Again, 1 plus 29 into A plus 29 square into B, and of course mod with the table size, right? Now earlier we were sure that these two values will surely collide. Now we can say, okay, the chances of the collisions are less, okay? So there is a less chance of collision, right? So these are the factors that you can keep in mind, that okay, if I'm building a hash function, can I modify it some way so that it reduces the chances of collision and it is fast to compute, right? So here also it is fast to compute, right? Maybe if you have a string in which the length is too big, maybe you can restrict that, okay, I will consider only the first 10 letters of the string for this weighted addition. That can also be done, right? So that will even make the function bit more faster, right? So if you are thinking that the keys are too long, you can restrict to maybe the first 10 letters or maybe something like that, right? So now we have a good hash function, which is the second one. So second one is obviously better. We are doing weighted addition, so it is going to reduce the chances of collision, right? But a collision can still happen, right? So how do we handle if still a collision happens? So here comes a collision handling scheme, right? So let us discuss about collision handling scheme now. So you have seen how do we design a hash function. Now we need to discuss how do we design a collision handling scheme, right? So collisions can still happen. We need to handle them, right? So let us talk about how do we design a collision handling scheme, right? Collision handling scheme, right? So there are actually multiple schemes, but I will particularly discuss one scheme, right? So in this case, what we can do something called as separate chaining. So we are going to discuss only one scheme. Uh, there are other probing techniques as well, right? So I will discuss separate chaining, right? So this is one of the most popularly and widely used schemes in implementing a hash table, right? Now I'll just copy the diagram that we have seen earlier. This is the diagram, right? So let me just copy it. Okay, so here we go. The idea is that if a collision happens, what should we do, right? That is what needs to be addressed, right? That we are going to address using a technique called as separate chaining. So suppose if we got dosa and it get mapped with index 4. So what we will do, we'll not store it directly inside this bucket, but instead every time we get a particular bucket mapped with dosa, we will start a chain from there, right? So what is a chain? A chain is like a linked list, so it's exactly a list, right? That means each bucket is actually going to hold the address of the first node of the list, right? So for example, I'm going to store dosa comma 100 here, right? Now suppose I got coke comma 150. So coke goes into the hash function, and maybe this time I get 2. So I will start a chain from 2, and coke will go here, coke comma 150, it will be stored here, right? Now suppose I got something like noodles, okay, and noodles is going to have a value, let's say 120. Now noodles, if it goes to the hash function, let us assume the hash function computes a index 4, right? Now at index 4 we already have dosa, so what we will do, we'll also try to store noodles at this index. How? So we can say, okay, we can add noodles to this linked list. Now suppose this is some address, let's say this is 150, this is 270, right? So this is storing 270, this is storing 150. So each array bucket is actually storing the head of the linked list, right? Now how we can insert noodles in this chain in order one time? It's pretty easy. So you can say, okay, I will create a bucket called noodles. Let's say this bucket is this node is created, so I'll create this node n with the given key value pair, right? So it's a new node with the given key value pair, right? Now in this new node, what should I do? Like how do I add this node in this linked list, right? So I can say, okay, this is some array, right? So or this is some table. So I can say array of and let us also compute the index. So I can say index where I want to store this is given by the hash function of the given key, right? So I get to know the index also. So at this index, I need to store noodles. So one thing I can do is either I can insert at head or I can do insert at tail. So since I'm not maintaining the tail of the linked list explicitly, but you can maintain if you want, I can also do a direct insertion at the head, right? So that means we can say, okay, this node 4 will refer to noodles and noodles will connect here. So right now this is connected here. So what I can do, I can ask noodles to connect with dosa, right? So I can say n dot next. So in every node I'm also going to have next field, right? So that I can actually form a chain just like a linked list. So every node is going to have a next field. So I can say, okay, you should connect here, right? So I can say n dot next should be equal to array of index. So array of index is storing 150, so that 150 will be copied here, right? And now I can update array of index to point to this node. So I can say array of index should point to n. So basically I'm changing this connection like this. So n is whatever it is. So this will be now referring to this node. Now if you look carefully, we have actually formed a chain, right? So this is, let's say this is some address, let's say 480. So this is now storing 480, right? So you can see we are actually forming a chain, right? We are actually forming a chain. So this is exactly how the insertion is going to work, and this is the code to insert, right? Do you think will it work in order one time? Absolutely yes. This insertion will be always order one, right? Because we are inserting something at the head of the linked list, irrespective of the chain length. The insertion will be always order one, right? So I hope you have understood insertion, but is it done? The answer is no. We are not yet complete, right? We have to still discuss one more concept, but that concept I will discuss after discussing searching. Okay, so this is still not complete. So this is insertion part 1, right? Okay, so there is something more to the insertion that is going to come up, right? Let us discuss searching, how we can actually search in such a scenario, right? So we are discussing searching now, right? So now what is the purpose of searching? The purpose of the searching is that given a key, I want to look up for the value of that particular key, right? If I ask, okay, I want to know what is the price of dosa, how I will find it? So first of all, dosa is a key. This is given as input. So dosa will go to the hash function. The hash function will generate an index where this dosa can be present. In this case, hash function gives me an index 4. That means now at index 4, I actually have a chain, right? If I write it little more clearly, so this chain looks like this. I have noodles, and which is like 120, and I have dosa, which is part of the chain, and this price is 100, right? And of course the next is null. Now I have to iterate on this chain to check if this chain can contain dosa or not. So if I iterate on this chain, I will find dosa at this particular position, and once I find dosa, I can return the value that is 100, right? That is how searching is going to be performed. So we first find the bucket where the hash function is telling me, okay, in this bucket you have to check, and in this chain dosa can be present, dosa may not be present, right? Now you might ask, okay, if we have to iterate the chain, then what is the time complexity of this operation? So my answer is it will be order of chain length, right? Now how do we figure out chain length? Okay, can this chain length become very large? The answer is yes, it can become very large, right? So the key to successful search operation is that we have to ensure that this chain length is very small. Okay, so we have to ensure that chain length is very small, right? Maybe 2 to 3 nodes, or maybe 3 to 4 nodes, right? And this is achieved using a concept called as rehashing and load factor. So we will discuss this concept. Ensure that the chain length is very small. So if the chain length is very small, we can say, okay, on an average this operation will be order 1. Maybe I say, okay, the chain will have only 3 nodes, 2 nodes, right? But now let us discuss how this chain length will be decided, right? How this chain length will be actually decided, right? Now suppose I have a hash table where I have 7 nodes only, right? And I keep on inserting data, right? So if I say, okay, my table size is 7 and I insert 70 key value pairs inside it, right? So what will be the average chain length? If I talk about the average chain length in this case, so I can say, okay, I have done 70 insertions across 7 buckets. So it will be 70 upon 7, that is 10. So 10 is a big number. I do not want to keep this much chain length, right? So this quantity that I've just written here, it is actually called as load factor. So load factor is a technical term for the average chain length. Okay, so how do we compute load factor? So we say, okay, total number of key value pairs that have been inserted into the hash table. So total key value pairs I have inserted upon my table size, or in other words you can say current size, the number of key value pairs that have been inserted upon table size. That could be another way of writing it, right? So I write, this one looks little more better to me. So in the current scenario, if you have 70 key value pairs inserted in 7 buckets, this is 10. It is actually huge, it's bad, right? So what do we need to ensure? We need to ensure that our load factor does not exceed a certain threshold, right? So in some languages it is 1, in some languages it is 0.7. So whatever is the case, we need to ensure that it does not exceeds the threshold value of let's say 0.75, right? Now what does it mean? So if I have, let's say, 10 buckets and I insert 7 key value pairs, so what will be the load factor? It will be 0.7. That means on an average every chain has less than one node, right? So that also means that my table size will be slightly bigger than the number of keys I want to put. So if I want to put, let's say, 100 keys, then my table size could be of the order 150, right? Something of that sort, right? So that is something we need to ensure, right? Now, how do we ensure that our table grows dynamically as the data in the table is increasing, right? So one thing you can do is, if you have an idea that, okay, I'm going to insert somewhere around 70 keys, you can initialize your table size um, around 100. Okay, so generally it is a prime number, right? So if it could be like 103, something of that sort, right? Or 107, right? So you need to ensure that if it is a prime number, it ensures slightly better distribution, right, of the keys, right? So what I'm going to do, I'm going to do insertions, and I'm going to show you how the load factor is going to change and what happens if the load factor exceeds the certain threshold. So going back, I'm going to discuss the insertion logic once again, and now, apart from doing the insertion in the chain, we will also discuss the concept of rehashing and how do we increase the table size dynamically. Let us talk about rehashing according to the load factor. Let us talk about rehashing, right? So rehashing is a mechanism that is going to help us expand the table size and bring down the load factor. Let us try to understand insertion and the rehashing procedure with the example. Okay, for example, now suppose I have a table which is of size 7, 0, 1, 2, 3, 4, 5, 6, right? Now I'm going to insert certain key value pairs inside it, and I will calculate the load factor during the insertion process. For example, I insert A, right? So the locations are decided by the hash index. So now the load factor will be 1 upon 7, which is 0.14, right? Which is well below the threshold. Okay, so our threshold is, let's say, 0.75. So it is below the threshold. I will not do anything. That means on an average every bucket has 0.114 elements inside it, right? If I say, okay, I will insert B, maybe it goes here. Now my load factor is 2 by 7, which is about 0.28, right? Then I insert C, maybe a collision happens and C goes here, but then on an average each bucket has now 0.42 elements, so it is 3 by 7. That is my load factor, right? And maybe I insert D, so it's going to be 4 by 7, right? So it's going to be around 0.56, right? So it's around 0.57 on the calculator. And similarly, if I insert, let's say, E, maybe E goes here, right? So it is 5 by 7, it's going to be around 0.71. It is still below the threshold. Then if I insert the sixth element, maybe F, it goes here and it collides, right? So it's going to be 6 by 7, which is around 0.85. Now at this point, what do I see? I see that the load factor, right, has reached 0.85. That means it is close to 1. That means on an average every bucket has around one element each, right? It is the time to grow the table, right? So what is the table? This is my table. I want to grow this table. I want to make it bigger, right? So what I will do, I will create a new table or a new array, right, which is approximately double of the given size, right? So maybe this table size was 7. So I generally look for a table size which is a prime number, right? So this new table size could be, let's say, 7 into 2 is 14. What is the nearest prime number close to 14? It could be 13 also, it could be 17 also. Let's say this is 17, right? So I'm taking the next biggest prime number, right? Now what I will do, this table is empty, right? This table is empty, and my goal is to remove all the entries from this hash table and put it into this hash table. Now you might ask, why can't we use this hash table, right? The reason being, your table size has changed and your hash index that we saw, right? So we saw it was a weighted sum. Okay, it was a weighted sum of the letters of the string taken mod with the table size. Now table size has changed, so my hashing will also change. That means if I now insert a, earlier it was going at position 1, now it might go at certain some other position. So a might go here, c might go here, b might go here, and d might go here. And since the number of buckets, they have also increased, that means my distribution uh, will also change, and it is possible that the number of collisions that are happening, they might reduce, right? So what I have to do, I have to do rehashing. So this is what rehashing is. So we have created a table of size double the capacity, right? And we iterated over every chain in the original table. Every node we added again into the hash table. So once we are done, what we will do, we will delete this from the memory. This will be cleared off, and now my hash table is going to refer to this table, right? Now in this table, if I compute the load factor, okay, if I compute the load factor now, this will be much lower than 0.85. Why? Because it was now 6 by 7. Now this will be 6 by 17. So if I calculate this value, 6 upon 17, this value comes out to be 0.35. 0.35, right? So I can keep on adding more entries into this table, right? Again, if again it exceeds the threshold, what I will do, I will execute rehashing once again, right? Now what I'm trying to say is that this rehashing is a special mechanism that will be triggered from the insert method when my load factor exceeds the certain threshold, right? So it will be some condition like, if my load factor exceeds the certain threshold, I will have to call the rehash method from the insert function, right? So this is something I will show you in the code as well, right? But I hope you're understanding the reason of rehashing, right? What is the importance of rehashing? So if we have done rehashing, right, can I say the average chain length will be always less than 1? That means on an average, no bucket has more than one node, right? So it might happen that some buckets may have 0 nodes, some buckets may have 2 or 3 nodes, but I'm going to say this average chain length will be a very small number, and it can be treated as constant. So that is why we say that our search is order 1 on average, right? Order 1 on average, right? That is what my search operation will be, right? Now another point, what is the complexity of rehashing, right? So of course we have to iterate on the entire table and put all the keys into the new table. So it is going to take order of n time, right? Then how my insertion can be order of 1? So if you look carefully, this rehashing is not happening again and again. So it is happening once in a while. So you inserted this element, we took order 1 time. This element, it took order 1 time, order 1 time, order 1 time, order 1 time. And at this point we saw that load factor is increasing, and it is going to trigger the rehash function. So it is going to hit order of n time, right? So can I say that for 6 elements I spent it constant time, but for one element I spent order n time, right? So if I talk about on average how much time I spent on each element, so again if I take an average, it's like a worst case, right? Inserting 6 is like a worst case. Worst case, yes, it can go order of n, but on an average we are spending order of 1 time in doing an insertion, right? You might ask, how can I bring down the time of rehashing? So if you know that, okay, I am going to insert about 500 keys, so you make sure in the beginning that your table size is big enough so that rehashing is never triggered, okay? Or it is triggered very rare, right? So the correct way to do it is initialize a large enough table. Okay, it should not be too big that you're using too much of memory. So you have to make a balance between effective memory utilization. So you should know from the historic data, okay, how big table should be sufficient. So if you're storing phone contacts, you know, in general people might have 500 to 1000 contacts, so you can initialize a table of the size around 1000, right? So it is just large enough so that rehashing is never triggered, right? Or it is triggered maybe just once, right? It is never triggered, right? So this is something we can do, right, to make sure that almost every insertion is order 1, right? So I hope you understood the concept of rehashing, and I'll show you in the code as well. Let us discuss the implementation of hash table. So I'm using C++, but you can also use Java or any other language to map the same functionality in your own language, right? So first of all, I discussed that hash table is a table, and in this table is going to contain the address of it is going to contain the head of the linked list. So linked list is made up of nodes, so a node will store key, a value, and the next field, right? So that is what I've defined in the node structure. So I'm using templated classes, so it's like generics in Java and templates in C++. These templates allow me to hold data of any t type in my node, right? For keeping things little simple, I'm assuming that my key is always a string, but it can be of other data types as well. For that also you need to use templated classes, and you need to provide a way to convert that data type into a hash index value, right? So for now I'm dealing with strings only, but I'm saying the value can be of any type. It could be int, it could be string, it could be float, because we are not computing any hash on the value. We are just going to store that value as it is. And third thing is the next property, that is of the node, right? Whenever I initialize the node, I set the value of key, I set the value which is the value, and by default I set the next as null, right? And this is my constructor. And if I want to delete a node, so this deletion will happen if I am deleting a certain value, or I'm doing rehashing and I want to delete some data, right? This is actually a destructor which says that if next is not null, delete next. So basically it is a recursive way of deleting the node, right? So that means if I make a call at this point, it says, okay, if I'm going to delete this node, and if the next is not null, first delete it. If the next is not null, first delete it. So it's a way in which I can delete the entire chain at once, right? So this is something which you can also like, uh, it can be implemented in other way also, right? So you might not necessarily do the same thing, but in my case I'm doing it. I will tell you why, right? So that is about the node constructor. And now let us come to the hash table class, right? So what I have done, I am actually keeping a dynamic array called table. So table is referring to an array, right? So you might ask why star star, because see, each bucket in this array is going to hold an address of the node. So it is of the type node star, right? And what is table? Table is a pointer to an array of pointers, right? Because each bucket is going to point to the head of the linked list. So each bucket is of the type node star, hence the type of the table is node star star, right? It is going to be a dynamic array referring to an array of pointers, okay? So I have a table which is not initialized at the moment. I have current size, I have table size. So current size will be 0 in the beginning. So I will show you the constructor for this. Yeah, this is the constructor. So whenever a new hash table is created, right? So current size is set to 0, table size is set to default size. I'm taking a parameter with the default value of 7. So if user gives me, let's say I want a table size of 107, it will be 107. But if nothing is given, by default I'm taking it very small and it is 7, right? Then I initialize my table array. So table is an array that points to an array of node star, and this is of size table size. So these many buckets I have initialized, and by default in every bucket I'm putting a value null, right? So this is null, this is null, this is null, right? So instead of having garbage, it is better to initialize everything with null. That is how that hash table has been initialized. I hope you don't have any doubts till now. Now comes the interesting method, that is insert, right? Now if I want to insert something, right? So my table is ready. So table is here. My hash function is also ready. Okay, I'll show you the hash function. Let's say I want to insert dosa comma 100. What do? I will show you the hash function. Let us understand the insert. So my key, that is dosa, it goes through the hash function and I get an index. So maybe the index is 4, right? So at this index, what do? I will create a new node. So I say, okay, there is a new node called n, which is dosa comma 100. So in this line, I do this work and I say n dot next, this is equal to table of index. So table, and this is index. So n dot next will point to whatever this is pointing to. So it is currently pointing to null. So the next starts pointing to null, right? Then I say table of index is equal to n. So this index is going to hold the value n. So n is, let's say, 248. That is the address of this node. So it is going to store 248, right? So this is how this node gets attached to the beginning of the table. Current size plus plus. So current size becomes 1. Then I compute load factor, so which is 1 upon 7. Is it greater than 0.7? The answer is no, right? So if it becomes, then I will trigger rehash. I will show rehash method also, right? So this is about the insert functionality, right? So I hope you're getting it. Let's say I'm inserting one more node which at the index 4. So I just want to show you how the chaining is going to work. Let's say I inserted noodles, and for noodles also I got an index 4. So noodles comma 120. I created a new node called n, right? Then I said n dot next is equal to table of index. Table of index is storing this value. So noodles starts pointing to this value, right? And table of index is equal to n. So this connection is broken and this starts pointing to this node, right? So you can see in a way we are forming a chain in which noodles is getting inserted at the head of the linked list, right? So this is nothing but insertion at the head of the linked list. Current size plus plus. So current size is 2, load factor is 2 by 7, which is again less than 0.7. So hence I do not trigger rehash at this moment, right? So I hope you understood the insert method. Next I want to show you the hash function that I've used here. So hash function, I've made it as a private. So what I'm doing, I'm simply multiplying the numbers. Let's say the word is dosa. What I'm doing, I'm iterating over this and I'm multiplying it with powers of 29. So it is 1. So initially it is multiplied with 1. Then in the next iteration, power becomes into 29. So into 29. Next time it becomes, power becomes again power into 29. So it gets multiplied with 29 square, and again it becomes 29 cube, right? So in order to avoid overflow, I'm doing a percentage mod at each step, because if you take mod at the last, uh, or if you take mod at each step, we know this is the property of mod. So mod can be taken at each step as well. So this is a better thing to do because it helps us to avoid overflow, right? I'm taking a mod with power also, and I'm taking the mod in the answer also. So I get an index which is in the range 0 to table size -1, because I'm doing a mod with table size. So I hope you understand the hash function as well, right? Now what I need to do is I need to understand the rehash method, right? So if we understand the rehash method, our insertion will be complete. So I have written a rehash method as well, which is actually a private method as well. So what I'm doing in my rehash method, that suppose I have a old table, like the actual table. In this I have inserted some keys. Let's say A, B is there, C and D is there. What do? I say, okay, old table is going to point to table. So this was my table. Now old table is pointing to this table. I create a new table, okay, which is almost double of the previous size plus 1. I'm just making it as an odd number instead of making it as a prime number. So I'm saying this is my table now, which is also the data member of the class, right? So what do? I initialize it with null. So all these values are set to null. And then what I copy elements from the old table. So I iterate over the old table. And how do I do the work? Let me show you. So I do it like this. I take a temp variable, which is the ith row. So temp starts from here. Okay. Temp is referring to the head of the linked list. And while temp is not null. So I copy the key, I copy the value. So I say, okay, give me this key value pair, and I call the insert method. So insert method, we know by default it acts on the table, which is the data member of the class. So it is going to insert automatically in the new table, right? And temp goes as next. So temp comes to this node. Again, I copy B, I and insert it in the new table, right? So once it is done, I make a destructor call. If old table of I is not null, delete old table of I. So in Java, there is a concept of garbage collection, but in C++, we have to use explicitly, we have to invoke the destruction of this entire linked list by saying delete old table of I. So I initiate a destructor call from here, which makes a call to A. A is being a recursive destructor, A makes a call to B. This way, this entire row is deleted, right? And then I go to the next row. So my I is increasing. So I go to this row, this row, this row, this row, this row. I do the same work, and all the nodes are inserted in the new table. And finally, I say, okay, I want to delete the array that is old table. So I also want to clear up this memory. So I say delete old table. This old table is gone, and since it is a local variable, this is also destroyed, right? So till now you have seen the insert functionality, and we discussed that the function rehash will be triggered from the insert whenever load factor exceeds the threshold. Okay, so we basically double the table size here, right? Now let us talk about searching a little bit. How do we actually do searching in a hash table? So searching is pretty easy. So if you have a hash table, right, and you want to search for a certain key, let's say dosa, so that key will go through the hash function. The hash function will tell you the bucket. So maybe this is the index of the bucket, and in this bucket there might be a chain in which dosa could be one of the item, right? So maybe this is some x item, some y item, some z item. So you need to iterate on this chain linearly, right? So I start temp from this node. While temp is not null, while I do not hit the end of the chain, I compare is the key of this node matches with the given key if I'm searching. So if that happens, I return the value. Otherwise, I go to the next node. If I hit end of the chain, that means I did not found the key, so I return null in that case, right? This is how searching is done, right? So on an average, what we are saying that this chain length is so small, right? Because of the rehashing and the load factor that we are maintaining, right? So we can say, okay, iterating over a very small linked list will take order one time on average. Okay, so we are not talking about the worst case. So a worst case scenario might be like this. A single bucket has all the n nodes inside it, right? So basically chain length is of the order n. But this is a very less likely scenario because this can be only possible if your hash function is too bad. It is producing the same bucket for many different types of keys. Okay, in general it's not going to happen. So that is why we say on average it's going to be order one most of the times, right? So I hope you have understood the search functionality as well, right? On a similar lines, you might have to do erase as well. You might want to delete a particular key as well, right? Now how you have to do it? Now this is pretty simple. If you know how to search, then you can also know how to delete, right? So suppose I want to delete a key that is y. What I will do, I will pass y to the hash function. It will give me the index. I'll find this linked list. Now the problem boils down to deleting this node from the linked list. Now you have to handle these cases. This node could be the last node in the linked list. It could be middle of the linked list. It could be beginning of the linked list, right? So if you know deletion in a linked list, you can easily handle the code to erase a particular key value pair from the hash map as well. So I hope you have understood the fundamental methods associated with the hash map, insertion, deletion, and searching. I hope this video helped you to understand the internals of the hash table. Before you leave, make sure you like the video, hit the subscribe button and share it with your friends. I'll see you next time with more insightful videos.